Hey everyone, and welcome to The Explainer. So if you really want to understand exactly how enterprise-grade AI is actually being deployed out there in the real world right now, well, you're in exactly the right place. Today we're diving into a genuinely fascinating case study coming from Orange Innovation. We're going to open up the hood on their real-time security operations center platform, their SOC, and unpack this central, maybe a little counterintuitive thesis. The idea that the absolute best way to deploy cutting-edge, multi-agent AI is actually by using, well, quote-unquote boring, ultra-reliable cloud-native Kubernetes infrastructure.
Which, of course, brings us right to the elephant in the room. Why build agentic AI on cloud-native foundations at all? I mean, for years now, the biggest bottleneck in security and platform teams has just been human rule authorship, right? If you want to scale up your threat detection, you literally have to go out and hire more analysts to write more rules. It's a huge constraint. But what if we could offload all of that heavy lifting? Imagine if rule authorship didn't have to be a human bottleneck anymore. To actually pull that off safely, though, we need the right battle-tested architecture, not just, some flashy AI demo running on a laptop. Okay, let's dive right into this. Here is our roadmap to see how Orange Innovation completely transformed their operations. First, the Agentic AI blueprint. 2. Agents as microservices. 3. Enforcing safety with policy. 4. Gating LLMs and observability. 5. The human in the loop. And finally, number 6, why cloud native wins.
All right, kicking things off with Section 1, the Agentic AI Blueprint, organizing the chaos.
So, picture a highly regulated production environment. It's a lot to handle, right? How do you even begin to structure an AI for that? Well, here's their basic fan-out structure. You have this central coordinator agent, and its whole job is to orchestrate a team of specialized agents, detect, analyze, remediate, and notify. The ultimate goal here is to shift all that heavy lifting of threat detection away from your tired human analysts and hand it over to a stateful, LangGraph-powered agent layer, meaning these agents can actually maintain memory and handle some seriously complex reasoning across multiple steps. It's like a highly coordinated digital strike team.
Now, to get all these agents talking to each other and interacting with the environment, they need a rock-solid communication layer. Orange chose A2A, which is agent-to-agent, and MCP, the Model Context Protocol. But honestly, the acronyms aren't the main takeaway here. What really matters is that these are open-source protocols, and they're governed by the Linux Foundation. By choosing durable, open governance protocols like these, operators can actually plan a confident 3 to 5 year enterprise deployment. You completely bypass that fear of getting locked into some proprietary ecosystem that might just up and vanish next year.
Moving on to Section 2, Agents as microservices, and why we are ditching in-process modules.
This right here is our very first big do this, not that moment for running LLM agents in production. Over on one side, you've got in-process modules. Sure, this is exactly how you'd build a quick AI demo on your MacBook, just cramming all your agents into a single process. But whatever you do, don't do that in a production environment. Because if just one agent gets stuck hanging on a model API timeout, boom, it drags the entire system down with it. Instead, the clear do-this approach is deploying them as standard Kubernetes workloads, treating every single agent as its own separate deployment, utilizing standard horizontal pod autoscaling, setting resource limits, using namespace isolation. Essentially, they just behave exactly like any other microservice.
Now, what's really interesting about this setup is how they actually handle that agent-to-agent traffic. Think about it. These AI agents are constantly passing around proposed detection rules and response actions. That is highly sensitive data. But instead of slapping on some massive, overly complex service mesh to deal with it, they keep it lean. They issue per-agent identities using Cert Manager, and they secure that traffic right at the kernel level using Cilium MTLS. They basically put a super tight lock on which agents can talk to which services. It's materially simpler to manage, but still incredibly secure.
All right, Section 3, Enforcing Safety with Policy, OPA over LLM Prompts.
We have got to talk about safety, because it is absolutely paramount here. When you have threat analyst agents mapping events against the MITRE ADTF framework, and they're out there proposing live firewall changes in a real production environment, yeah, you need an ironclad safety tier. Which brings us to this massive aha moment from the platform's architect. Quote, "The instinct is to put safety constraints in the reviewer's system prompt. Don't. We've literally all tried this, right? Telling an LLM, hey, you're a helpful assistant. Whatever you do, please make sure you never do X, Y, or Z. But at the end of the day, LLM Pros is just way too unpredictable for actual production safety. A prompt is not a firewall, folks.
So, if a prompt won't work, how do you actually constrain the AI? The answer is deterministic policy as code.
They use OPA, that's the Open Policy Agent, alongside Kyverno admission rules. So the AI reviewer agent doesn't just guess if an action is safe based on how its prompt was written. No, instead, it makes a direct MCP call to OPA to get a strict, unit-tested verdict. The safety measures are version-controlled, they're code-reviewed, and they are wonderfully, boringly reliable. It completely strips away the guesswork and makes AI safety 100% deterministic.
Let's jump to Section 4, Gating LLMs and Observability, how to control the chaos and the costs.
Okay, let's see how this all builds up. Dealing with millions of real-time security events is a massive operational hurdle, especially when you factor in the sheer cost of LLM tokens and trying to observe the whole system. So they set up this brilliant three-step pipeline. Step 1. Falco eBPF intercepts system calls directly at the Linux kernel level on the workloads they're monitoring. All those raw events flow right into Kafka. Now obviously, if every single one of those events triggered a heavy LLM query, you would literally go bankrupt by Tuesday. So they put in Step 2, a classical machine learning filter known as an isolation force. It acts as this ruthless gatekeeper, filtering out all the normal day-to-day noise before the expensive LLMs are ever even woken up for Step 3, which is the agent fanout. Take a look at that number right there, 17. That scikit-learn isolation force model actually scores 17 distinct features in mere microseconds. It's incredibly fast. Only the absolute tiniest fraction of events, the ones that look genuinely novel and score above a highly calibrated threshold, only those get passed along to the AI agents. It is just a fantastic way to tightly bound both your per-event latency and those runaway token costs.
But of course, when the AI actually does decide to act, how on earth do you track it? Well, observability rides the A-to-A trace ID. Every single agent emits these clean, structured JSON logs stamped with this trace ID. Those are scraped up by Prometheus, visualized by Hubble, and it gives you this beautiful, crystal-clear map of the network flows. You can retrace an entire AI reasoning chain in minutes. And, maybe even more importantly, all of the agent prompts, the tool lists, the output schemas, they're all strictly managed via GitOps using Argo CD. This is huge because it completely prevents that infamous random Jupyter Notebook prompt disaster that I'm sure we've all run into at some point. Updating an agent is no longer a Wild West scenario, it's just a standard, fully audited, easily reversible pull request.
Moving into Section 5, the human in the loop, making it protocol, not just a culture.
So you might be wondering, how do the actual SOC analysts and the platform teams interact with this highly automated beast on a day-to-day basis? Well, the crucial point is how they handle gateways. Every single consequential decision hits exactly 3 deterministic terminal states: auto-execute, auto-reject, or escalate to a human via Mattermost. And when it does escalate, it brings the receipts. The human gets the full reasoning chain attached, along with ChatOps commands so they can approve or dismiss right there in line. Human escalation isn't just some vague, nice-to-have cultural idea of, oh, we'll have an analyst double-check it later. No way. It is a strictly version-controlled policy state that automatically fires whenever confidence is too low or the potential blast radius is just too high. It's literally baked into the protocol.
And that brings us to Section 6, why cloud native wins, the final verdict.
Let's just bring all these threads together to really prove our core thesis here about capacity and scale. This table brilliantly illustrates the setup. Look at the exact mapping of standard cloud-native tools to these specific agentic AI jobs. Kubernetes, it handles agent deployment and isolation. Falco, it provides the syscall detection substrate. Argo CD, that manages the GitOps for your AI prompts. And OPA and Kyverno, they enforce the deterministic safety policy. By mapping these proven, standard cloud-native tools to these specific AI jobs, Orange Innovation completely transformed their SOC operations. It went from a headcount-bound problem where scaling up literally meant just hiring more people to simple replica scaling. Need more capacity? You just deploy more agent replicas and tweak your policies. It's that elegant.
Which leaves us with this final, genuinely provocative thought. Think about it. Agentic AI inherits basically all the exact same operational problems that cloud native already solved years ago. Things like identity, isolation, policy, and observability. So the real question is, are you ready to stop inventing parallel substrates? It's definitely something to chew on, right? It really challenges us to stop reinventing the wheel and to start diving deeper into the CNCF ecosystem to actually power this next generation of AI. Thanks so much for joining me for this explainer. I hope you found it as fascinating as I did. Keep learning, and I'll see you next time.